All right, so this is just a little bit of a discussion about page 10, number 4, and then just sort of an overview before you maybe move on into page 12. This whole packet is due, I believe I made it due Monday. Might need to double check on that, but not this week. So we're going to look at number 4 because in years past that one's been an issue. So the function f is a cubic function given by ax cubed plus bx squared. And we need to determine what a and b are. So we have two unknowns. And you should have learned in algebra 2 that if you have two unknowns, you need two equations. If you have three unknowns, you need three equations. Four unknowns. N unknowns requires n equations to solve for all of those unknowns. So we know that for inflection points of cubics, the second derivative has to equal 0. So that's usually where kids get one equation. They're like, oh, okay, I know that the first derivative would be 3ax squared plus 2bx, right? So consequently, the second derivative is going to be 6ax, bring again a and b are constants, plus the derivative of any linear term is just its coefficient. Makes sense because lines, their slopes are right. The slope gives you the slope of the tangent line, so it makes sense that the linear ones go to just the coefficients. But all right, so we've got the 0 equals, right? 6ax plus 2b. But that's only one equation, two unknowns. I'm in search of an a and a b, and this is usually where hands go up and they're like, what did I do wrong? And it's nothing. You just need to come up with another equation. So there has to be enough information up here for you to have another equation. You might say, well, they didn't tell me what the first derivative is. Nope. So there's nothing you can do with the first derivative. You can take it, but you don't know what to set it equal to. But look at what we haven't used yet. It has a point of inflection at 2 comma 16. So what that means is 2 comma 16 makes the second derivative 0, but it has to be on the curve. If it's a point of inflection of the curve, it has to be on the curve, which means its y value has to equal a times its x value cubed plus b times its x value squared. So that does give you your second equation. You have the 16 has to equal 8 a plus, and then we've got 8a plus, where did I write? There it is, 4b. And remember that point of inflection was equal to 0 at the point 2 comma 16. So I know that the x is 2 right here. So let's rewrite those nice. We have 0, it would be equal to 12a plus 2b. And we'd have 16 equaling 8a plus 4b. So this is what we need to solve. I'd probably take the top through by -2. Where can I write that? I'm going to go erase this. And we'll have the 0 equals -24a minus 4b. 16 equals 8a plus 4b. And I'll let you continue solving for a and b. So keep in mind that if you know what you need, if you know you need two equations, and you know you have an inflection point. So the first one comes from setting the second derivative equal to 0 at x equals 2, right? But we also know the point is on the curve. So there had to have been two equations hiding in there for you to solve it. So that should have kind of clued you in. So I wanted to look at this page again because we discussed the mean value, but never specifically Rolle's. But remember, Rolle's really is the mean value theorem for the specific case where for Rolle's, it says if the function's continuous and differentiable, and there's another caveat to that, with f of a equaling f of b, then there exists some place where the derivative equals, or the slope of the secant line is the same as the slope of the tangent line. But if on a curve, f of a equals f of b, their y values are the same, then the slope of the secant line is 0, so the slope of the tangent line is 0. So Rolle's theorem really just says that if f of a equals b, then the slope of the secant line is 0. So we're guaranteed some place where the derivative equals 0. So when this says check that Rolle's theorem holds, you're going to say, is f of -1 equal to f of 1? If so, you'll set the derivative equal to 0. And same here, it says, which does Rolle's, I forgot the R, for which does Rolle's theorem hold? Again, you're going to check, does f of -1 equal 1 on each of these? If so, are they continuous and differentiable on the interval, right? So it has that continuous, differentiable, and f of a equals f of b. All right, mean value. Remember the issues for the mean value function must be continuous. All absolute value functions are. Has to be continuous on the interval and differentiable on the interval. So for absolute value functions, suppose it's this guy, which looks like 1, 2, 3, 4, 5, this, it is continuous on the interval from -infinity to, let's say, 3. But it isn't on this interval because of the differentiability issue. So you have to figure out where the vertex is of that absolute value v. And if it's on the interval in question, then we're not differentiable on the interval, and therefore mean value theorem can't be applied. And we already talked about this. So that's it. Continue working in that packet, and peace out, Girl Scouts. Let's see here.